Alright guys, let's review enamine formation and subsequent acylation experiment, which is the last experiment of this semester. Firstly, let's talk about enamine. Enamine is an unsaturated compound derived by the condensation of an aldehyde or ketone with a secondary amine. Enamine are very versatile intermediate. They can react with a variety of compounds. And the general structure was shown here, right? There was also a question in the pre-lab quiz asking you which of the following compound is an enamine, right? Secondly, let's talk about the reaction itself and the details during the experiment. So I'm showing you the example reaction scheme with first step here. Make sure that you know the reagent's name and structure. So we started with cyclopentanone and pyrrolidine as a starting material, right? A ketone and a secondary amine. P-toluylsulfonamic acid was used as a catalyst. You also need to know the structure of that, as well as toluene as a solvent, so that you can form a possible enamine and water as a byproduct. If you can still recall that we used a very interesting, where we used a new apparatus setup for this experiment. It's called the Dean-Stark trap, right? So basically, you put cyclopentadiene, pyrrolidine, p-toluylsulfonamic acid, toluene into the round bottom shown here. And after heating, the reaction where the solution are going to boil, right? And you're going to use a Dean-Stark trap to collect the liquid in the burette part. You also want to make sure all the liquid refluxed back in the condenser. If I ask you to draw out the apparatus setup for this reaction, you will need to know all parts name. You may need to include clamps. Also, heating source. We used a heating mantle here, right? These are very important. And this is called the Dean-Stark trap, which is the most important part. During the reaction, you observed that a mixture of liquid are being collected in the burette part in the Dean-Stark trap. So now came the question, what is the mixture of solution? And why do you use Dean-Stark trap in the first place? You can kind of see in Dean-Stark trap as an upgraded reflux setup, right? So you're collecting liquid at the same time. You're collecting a volumetric amount of liquid at the same time, condensing all the solvent back. If you compared all the boiling point of the starting materials, solvent used, you may realize that except the starting material, water have a very low boiling point, as a matter of fact, lower than p-toluylsulfonamic acid, which is 140, and lower than toluene, which is 110, right? So you're collecting actually the byproduct of this reaction, water, in the liquid, in the burette part, in the Dean-Stark trap. It also helped to push the reaction to the right to completion, right? However, when temperature goes up, a small amount of toluene are also going to be collected in the burette part. Since toluene and water are not miscible with each other, they also have a different density, right? They're miscible with each other. They're going to be boiled out at the same time, and toluene having a lower density are going to be taking the part of the top layer, while water are going to be at the bottom layer in the burette, right? So here is water, and the top layer are going to be toluene. And this is going to be brought back to the round bottom, okay? So we use the Dean-Stark trap to get rid of water byproduct. At the same time, you don't want to lose any solvent, which is toluene, right? You also want to make sure the reaction happened at the boiling point of toluene, which is 110. All right, then after the formation of the enamine, you react that with a ethanoic anhydride. After condensation and get rid of water, you are going to be producing the two structures I'm showing you on the right. They tautomerize with each other, they're isomers with each other, so you might have a mixture of both. And as a matter of fact, you are seeing both the presence of both structure in the proton-NMR spectrum. So in the proton-NMR spectrum, you're asked to identify which one is it. More than half of the class identified it wrongly as the first structure. As a matter of fact, you're producing the second one. And in one of the post-lab questions, it's asking you, what is the peak at 3.4 ppm? What does it represent? It's also kind of a hint, to suggest you might make the wrong prediction based on the proton-NMR analysis. The peak at 3.4 ppm, which is a triplet, will suggest this proton in the diketone product, which was not integrated. We designed this experiment to give you an idea of kind of what the real-life research was, and also to make the right prediction based on spectral analysis rather than your prediction. And last but not the least, here's a mechanism. I'm not going to go through the very detail, but you can use this to compare with your mechanism for this experiment. I'm going to scroll very slowly so that you can take a screenshot. The base used will be pyrrolidine. It's a base. I don't want to repeat it, so I used B to represent it. The green part will be the second week experiment, which is the isolation part. A reaction mechanism needs to be drawn in a stepwise manner. Intramolecular electron or proton transfer are very unlikely, so you may want to draw them stepwise. Right, in the end, you have possible a mixture of the two products, and they tautomerize with each other.